All right, thank you for joining us today. My name is Eric and I'm your presenter for today's session. Now we are going to have a webinar about model-based design. There are four topics that we prepare for you over four separate sessions. We will start with control design made easy today, followed by plant modeling on the next session. Now I'm going to share with you control design made easy with model-based design or MBD for short. The key takeaway at the end of the session that you will able to first know how to design and validate controller effectively using model-based design or MBD. Then you have understanding on closed loop simulation and controller optimization, thus reducing the development cost and time through simulation-based tuning. Here is the agenda for the session. If you just getting started with Simulink or control system, don't worry. I will mention you how to get started on the end of this session. And I will start with the overview of the model that include what is model-based design, why we use this approach. Afterwards, I will show you the typical control design workflow and options that are commonly used, for example, PID controller and compensator design, where you can design your controller using transfer function. We describe model-based design as systematic use of models throughout development process, and there are two major components. The first one is modeling and then followed by automation. Modeling with simulation and analysis to try out new ideas and give you fast, repeatable tests, and automation of coding and verification to take out manual steps and reduce human error. Before we jump into the model-based design workflow, let's set the stage by looking at some drawbacks with traditional development process that can cause design delays and cost overruns. Traditional development process involve heavy investment on building physical prototypes, which is very expensive, time-consuming, and prevents rapid iteration. On the other hand, creating and simulating virtual models enables complex design space exploration and continuous design improvement and is much cheaper, faster, and safer. However, spending on simulation has been relatively low. If we take a look on the scenario where there is no model-based design, it will start with a set of requirements to determine what is the functionality is. And from there, it needs to satisfy this requirement and build the architecture and then do the design. From the architecture, it will implement the design in software and then integrate it and then test the entire system. Each stage produces artifacts such as requirement docs, paper specs, physical prototypes, hand-coded algorithms, and testing artifacts. When the system in design is complex, it becomes more and more challenging to manage the artifacts because there can be a split between the different teams and that are responsible for these different phases. It is also hard to make changes because the barrier make it difficult to move back and forth and communicate between different phases. So requirement traceability is poor because they are defined early in the process and can get lost if there is no strong linkage to the subsequent phases. A lot of manual steps are involved across different development stages, especially hand coding and manual testing, and they introduce inconsistency and slow down the development. In this process, the errors are often discovered late in the process as you make more progress and it become more costly to fix the issues and it's become more and more time consuming. As a consequence, the cost runs over the budget and the project encounters delays. With model-based design, it helps restore the balance by reducing waste from creating a physical prototype and placing a stronger emphasis on modeling and simulation, which enables you to spin your development faster by rapidly prototyping and testing the new ideas. With model-based design, multi-domain models serve as the source of your design throughout all phases of the development, so that you can eliminate the barriers between different development stages by promoting understanding and communication of work across different teams. Models at the center of your development process to create a digital thread that enables requirements capture and full artifact traceability. So the models can help you to chapter the requirements, specify the system behavior and architecture, perform simulation, and provide a foundation for automation with model-based design. So you can automatically generate the code from your models for the implementation and test and verify your component and system continuously to identify and fix the issues early rather than late in the process. You perform the requirement verification and early design verification on your modules. Just as you start to formalize your design from specification and architecture. Once the design is verified, you can perform the virtual integration testing, such as software in the loop, hardware in the loop, and processor in the loop, before you move on to the physical system. Modeling and automation allow you to eliminate inconsistency, manual step, and human error from your development workflow so that you can focus on your time on what truly matters, which is creating innovative design solutions. In summary, modeling and simulation enable short and agile iteration cycles, save times and costs, and ensure the deliverability of the products with minimal defects and high quality product result. So from there, let's take a look on the one of the study case from Korea Institute of Machinery and Materials, KIMS, who developed a prototype of maglev-based anti-rolling system for mobile harbor. The challenge that they encounter is the system requires two complementary controllers, and it typically take 1 to 3 years, but the anti-rolling had to be completed in just 3 months. Imagine that. So from there, MathWorks provide the solutions such as simulating to simulate the control system, and they also can generate the C code from there right away without manual coding. Thus, development time reduced by 70% and 20,000 USD more potential prototyping cost saved. Therefore, they have confidence in the in design performance. Okay, now let's go on to the next agenda, which is the workflow of typical controller design. To start designing a controller, you need to aware of its workflow. Let's start with the design part. Here, you need to define the plant and the controller itself. For plant modeling, it will be explained in the next session, so stay tuned. For the controller, we will talk about this on the next slide. Once you have the design ready, then it's time to implement it in a prototype, then tune the controller until it's satisfied to your requirement. Also, don't forget to do the testing and verification to make sure that last change are still complies with the requirement and intended standards like ISO and IEC. From there, we can simplify those into 3 stages, which is build, tune, and simulate. To do that, there are 2 approaches. Do the tuning directly on PID controller or use a compensator. Now let's start with the PID controller block. And we are going to take a look on one of the use case, which is um, a damped second order continuous system. It's actually a damped spring and we are going to control that to make it have more faster response. So if we double click on the PID block, you will see that there is multiple parameters that you can tune either manually or automatically with this tune button, and we will talk about this on the live demo soon. Other than that, you can have an adaptive approach, which not really involves any tuning. So the controller can tune itself adaptively, and this is great for dynamic system that need to be tuned over time. So once you have decided, you can do the simulation right away on Simulink or use hardware to have bidirectional data transaction between your simulation and the real hardware. Now let's take a look on the live demo. Now I'm opening my MATLAB. This is my this is my first display of seeing the MATLAB. So if you have a different layout, you can go to this layout button right here and choose the default layout right there. And now let's start this Simulink environment right away by clicking this Simulink button. Okay, I'm starting the Simulink. And now I have the start pages here. And from here, we can start from the blank model. But if you want to go fast, there's actually a boilerplate for the controller system. So we can go search for, let's say, PID, and it will suggest for feedback controller, which is what we want to do. And from here, we can see that this is matches with our diagram as you see on the previous slide. Now let's create model from there, and I have the model open right away. So I'm hitting space to zoom it, and now we have controller and the plant. Those are subsystems. Now let me go into controller subsystem, and we only see PID because our control is just PID. To make it looks more better, I can actually go back and right click on the controller subsystem and then click expand subsystem. And now we have PID controller right here, right away. For the plant model, we are not going to talk about this much because we will have a separate session on the next, which is about plant modeling. So stay tuned. And now all I have to do is just add a scope right here. So I'm going to zoom out a bit and then double click and search for scope. And from there, I just have to connect the scope to the measured output. But I'm not only limited to reading the measured output. I need to see also the reference. So I just have to right click on the reference right there, right click, and then put it into the scope. And perhaps a little adjustment for the wire to make it looks more better. And that's it. So let's take a look on the resulted signal by double clicking the scope. Now this is the scope. Perhaps I'm going to adjust the system a bit so we can see both sides. Now we have the scope on the right side of the screen and the model on the left. And now I'm going to click this green start button to see the result. And now it's running the simulation. And surprisingly, it's run very fast. You can do the same thing also. Now we have two lines here, the yellow one and the blue one, which is what? Now we can click the view right here and then click legend. And from here you will see two color which with their own labeling. So basically, yellow is the measured output and blue is the reference. The goals of this model is we want to make the yellow line as close as possible to the blue line. So this is what the controller actually doing. To do that, we can double click the PID block right here and take a look on the existing parameter that we can adjust. So from here, you can either manually adjust the PID coefficient. So basically, PID controller is a mathematical way of doing control, and you will see that there is a transfer function right here that represent the PID control. And all we have to do is just to adjust P, I, and D coefficient and optionally filter coefficient. All right, from here, you're not only doing that manually, you can actually do the automated tuning right there. And there is two methods available for you to be chosen. So you can do frequency response based or transfer function based, which involve an app. For now, actually, you can use a frequency based because the system has a single frequency like this, but you can also use the transfer function base. For the frequency response base, you'll be greeted by another diagram. So for now, I need to apply the model because it requires you to have the latest model saved. Now I already click apply and then click tune once more. And now it's showing the diagram, the dialog right here. You can either click the tune button right away or tune the experiment setting. And basically it's trying to do the like manual tuning but fully automatic. And actually it's pretty straightforward. And there is another way which is using transfer function base. So you will okay, I'm going to click apply once more. You will see another uh, another kind of like dialog. Actually, it's an app, and from here you will you can do the tuning way more efficient. It, either it have a single frequency or multiple frequency, which is very convenient. So from here you can see there is two line. The first line is the dash line, which is represents an original signal, and the solid blue line is the tuned signal. And we are going to change the blue line right here by dragging the slider over there. So once you drag the slider, you will see that the signal is now have faster response. Just don't overdo it or you have drifted signal. Okay, from here you can make the best fit of your signal. And I noticed that this is the best setting I can have. So all we have to do is just click that update button and it will automatically change the value on here. Ta-da. All right, now I'm going to just have to close it. And from here we can see the updated signal, what it looks like. Now I'm replay the simulation once more and we see that the result is now way more matches with the reference, which is very good. Well, actually, it's not really that perfect. If you take a look on here, there is a minor overshoot. So I'm going to tell you another approach of tuning. And let me go back to the slide. So actually, you can do another way of tuning, which is using signal constraint block. So it's an additional block that can be used to make your controller follows your requirement. So from here, you just have to add a signal constraints block, and then you can tune the requirement over there. Once you have inputted the requirement, click response optimization button, and you will see a plotting like this. So basically from your signal, the blue line, you can match it with the black line, which is your defined constraint. And not only limited by that, you can add your own variable, not just limited by P, I, and D. You can add something from the plant. So that means that you're not only tuning the controller, you can also adjust another thing like the plant. Now let's take a look on that alternative approach. Now I'm going to go back to the MATLAB, and from here I'm going to open the existing models with the existing requirement. Now I'm hitting space, and you will see that there is an additional blocks right here, which is signal constraint. And you can actually retrieve that from by double clicking here and search for signal constraints, or you can go to library browser over there on the top and search for signal constraints inside the design optimization right there. Now I'm going to zoom it a little bit, and you will see that inside Simulink design optimization, there is signal constraint, and then you could choose check step response characteristic. And that's how you can add it. Now from here, we can double click the block and then set the requirement. Now I already have set the requirement, and go to response optimization to see the plotting as you saw earlier in the slide. Now we have the plot open, and this black line is your defined constraint. You can either adjust that from previous dialog, or you can drag the black line to suit your needs. So let's say from the diagram you feel like, that's not really, it's too fast. So you can drag this black line and it will adjust the requirement for you. And then from here, you can also plot the model. So basically it's running the simulation, and then it will show the blue line right there, which is representing your current signal. And then from here, you can add some variable like PIND, but for now, I need to create that variable inside this PID block by double clicking this PID block. And then from here, you notice that there is 3 dots over there. Just click it and name the variable. Let's say I just want to call it KD. This one is KD, or yeah, KI. And this one is KD. And perhaps the additional one is filter coefficient, and I just call it, let's say, KM. Hit OK, and then I'm going to go back to the app and then add the design variable right there on the top, and then click New. And from here, I can add the variable. So lastly, I just add KP, KI, and KD, and KM, and add it into continuous as a continuous variable. Actually, you can define your constraint right here, minimum and maximum, just like typical optimization task. But for now, I'm going to leave it infinity as a default value. Now I just have to click OK. And from there, we can do the optimization by clicking this green button. But for now, I'm going to leave it, let you try yourself, because there is another thing that I want to share, that I want to tell to you, which is compensator design. So this is actually another approach that you can do other than last two method, which is using compensator or AKA transfer function way. So from here, you can add your transfer function block or TF in short, and you can do the same control system designer. And from there, you could define which transfer function to be optimized, and from there you could also choose way more diverse the tuning method and also the plotting. And the greatest thing is you're not only limited to step and body plot. You can actually add another plot in case you interested to know deeper in control system. You can add something like Nyquist, Nichols, etc. And then from here you will have your system optimized with just transfer function. Okay, I noticed that there is a question: what's the difference between this approach and PID tuning approach? Okay, that's a good question. So basically, if you are familiar with transfer function, you want to use this compensator way. Other than that, you want to use the PID controller directly, or perhaps using the signal constraints if you have specific requirement. Okay, I hope it's answering. It's answering. If you feel have anything that need to be mentioned, let me know in the chat section. All right, all right. Thank you. Now let's move on to the next case. Next case, which is multi-loop tuning. So let's say you have a scenario where you need to create a complex system, which is, let's say, a robotic arm. From here, you need to tune each of these degree of freedom. Let's say you want to tune the wrist part, and then you tune the forearm. The problem is, once you have done tuning the wrist part, there is no guarantee that it will be the same after you tune the forearm. So if we model that, it can be modeled as a parallel, and it will be very painful to tune, let's be honest. But don't worry, there is a solution for that. Say hello to SL tuner function, which can help you to tune everything at once and pick the right P, I, and D coefficient for you on the phase Y simultaneously. So if I repeat the video, you will see that the robot is now way more agile than than the previous way. All right. So from here, we can have several takeaway on how to design and validate effectively using MBD. So you have an idea on simulating a closed loop and optimize your controller, thus reducing the development cost and time through the simulation-based tuning. Also, as an additional information for you that just starting using Simulink for control system, I will tell you a bit of information for that. So if you go to networks.com and you go to, let's say, help center, you will notice that there is 3 dots over there. Go to that 3 dots or 9 dots, three times three, and go to online training right here. Don't worry, the training here mostly are free, especially if you take a look on this on-ramp. All of these on-ramp are free for you to try. So let's say you have a knowledge on MATLAB and you are new to Simulink, so you can go to this Simulink on-ramp and it will notify you that it require basic knowledge of MATLAB on-ramp. So if you're not having this one, you can start with this first. So basically from here, it's not only showing you a video, it will also have an interactive course. So actually it feels like you have running MATLAB on your browser and it has several instructions like this to follow. So you have an idea on how to implement your idea on Simulink. And actually that's pretty fun to do. Feel free to try. Okay, if you interested to other topics, you can go to our site on www.techsource-asia.com/events. So you can attend some seminars, webinars, hands-on workshop, trade shows, and join us on YouTube, LinkedIn, and Facebook page. I think that's it. Thank you for your time for joining us today. I hope it's useful for you. If you have any question or if you need guidance, feel free to contact to us. And once more, thank you.